good day. So we will have another example for our series, Shear and Moment diagrams. Okay, so this is actually the part 9 of our lecture, and this will be the 7th example. Okay, so unlike our previous example, we will have an example about cantilever beam. Okay, without further ado, we'll try to solve this one. Okay, so cantilever beam is a beam in which one side is fixed and the other side is free. Okay, so we all know, okay, from our statics that in a fixed support, we have three reactions. We have a horizontal reaction, a vertical reaction, and then we have the moment reaction. Okay, so let us assume first the direction of our three reactions. Okay, so here I assume that your AY is upward, your AX is to the to the right side, and your MA is in counterclockwise. Okay, so this is our initial assumption. So if we get during our when performing a summation of forces vertical and horizontal and summation of moment, and it turns out to be negative, so the direction will be reversed. Okay, so here, okay, without further ado, we're gonna try solving it. Okay, so first, the very first thing to do is sum up forces. Okay, so let us say start at horizontal. Okay, summation of forces x equals to 0. Let us say to the right as positive. So we have, since there is no other horizontal forces we can see here, so ax is equal to 0. Then another one, we have summation of forces vertical is equal to 0. Okay, so let us assume that upward is positive. And we only have one reaction, which is AY. And then we have the loads, 80 kilonewton point load, and then the 25 kilonewton distributed load. Both will be negative since they are downward. So 25 times 3 equals to 0. So we get the value of AY. So AY will be 80 minus plus 25 times 3 is equivalent to 155 kilonewton. I know, this is actually 6. So 25 times 6 is 150. So this is 230 kilonewton. Okay? Using simple algebra, because when you transfer 80 to this point, it will become positive. And when you transfer negative 25 times 6 on the right side, you get positive. So we have 230 kilonewton. Since we get a positive value, so it is upward. And then the next thing is we sum up moments equals to 0. Okay, so let us choose, okay, the most convenient side to sum up moments with is on the fixed side. Since, okay, so sum up moments at A is equal to 0. Let us say counterclockwise as positive. Okay, we have, okay, please remember that we have a reaction of MA at the fixed support. So we have MA, okay, minus the 80 kilonewton load. Okay, so since this 80 kilonewton load relative to A, okay, relative to A, this 80 kilonewton load will make this beam turn clockwise, so it's negative because we have assumed counterclockwise as positive. So negative 80 times 3. And this distributed load, 25 kilonewton meter, so since it is relative to A, it tends the beam to rotate counterclockwise, so it is negative also. So we have negative 25, okay, the total length, which is 6, and then the centroid. The centroid of a rectangular uniformly distributed load is the length over 2, and the length is 6, so 6 over 2. So we got the value of MA. Okay, 80 times 3 is 240, 25 times 6 is 150, times 3, 450. So we got MA as 690 kilonewton meter. And then we got since we got the positive answer, so our assumption of counterclockwise reaction is positive. Okay? So let us check it with the calculator. Okay, 690. From now, okay, from after that, we can proceed to drawing our shear and moment diagrams. Okay? So we can actually solve this even without using shear and moment equations. Okay? So if you want to solve it using shear and moment equations, then you have the freedom to do so. Okay? In this case, it is just a point load and a rectangularly distributed load, so we can easily track its shear and moment diagrams without using. Okay, I just put here the reactions. This is 230. Okay, 230. So this is your shear diagram and your moment diagram. Okay, so please remember. Okay, so the shear here, it starts equivalent to your vertical reaction. So here, your Vx is 230 kilonewton meter. 230 kilonewton since. And then, the next one is, what will be the shape of your shear diagram since we have a distributed load. So since we have a distributed load, rectangular, so the shape of your shear diagram will be impending downward. Okay? Linearly impending downward. So, it will be linearly impending downward from this point up to 3 meters. Okay? So, we have 25 kilonewton meter. So, we get the value. Okay? So, I guess we get the value. Okay? 230 minus 25 times 3. 230 minus 25 times 3, 230 minus 75 is 155. So, we get here 155 kilonewton. And since we have an 80 kilonewton load downward, so we'll go down 80 kilonewton from 155. Okay? So, let us say 155 minus 80, we get 75. So this will be a linearly downward 75 kilonewton. And since we have another distributed load after 3 meters, which is 25 kilonewton, so its direction will be impending downward again. And then this is actually 0 degree curve, so this is a 1 degree. So this will be, okay, so this will be a linearly downward. Okay? 1 degree curve. Okay, 1 degree. So this is your shear diagram. Okay. And then let's go to the moment diagram. Okay? Here, please take note, unlike the simply supported beams, we have a moment load at the supports. So since we have a moment load at the supports, we try to see what is its direction. Okay? So if it is clockwise, it is positive. But if it is counterclockwise, it is negative. Since we get MA as counterclockwise, so it's negative. So we have 690. Okay? No more assumption. Okay? It's always the case. If it's negative, it's counterclockwise. If it is positive, so if it is, if it is counterclockwise, it's negative. If it's clockwise, then it's positive. Here, we got counterclockwise moment, so it's negative. And then, remember that the area under the shear is equivalent to the moment. But somehow, we have an initial moment of 690, so we have negative 690 first. And then add the area uh, under this diagram. If we want to get, okay, if we want to get the moment at x is equal to 3. Okay? In order to get the moment at x equals to 3, so we got to add the negative 690 kilonewton meter by the area of shear diagram from x to equals to 0 to x is equals to 3. Since it is trapezoidal, we all know that the area of the trapezoid is 1/2 h times b1 plus b2. Okay? Remember your 1/2 h times b1 plus b2, remembering your geometry. So we add 1/2. The h here is, okay, the h here is the 3. Okay? Since, and then the b1 here is 230, and the b2 here is 155. So we get the moment at 3. Okay, we have negative 690 plus 0.5 times 3 times 230 plus 155 equals negative 111, 112.5. So, since it is 1 degree, so our and positive, okay, it is a positive area. So the form of our curve will be like this. Okay, this is negative 112.5 kilonewton meter. And then again, we have this area, which is 75 kilonewton and triangular. Okay? So since we get negative 112.5, we will use this in order to solve, okay? In order to solve the moment at x equals 6 or at the end point. So we have an initial value of negative 112.5. So we add to this area, which is 1/2 times, okay, area of the triangle is 1/2 BH. So here we got also 3 meters here. So 1/2 times 3 times 75. Okay. So we have plus 0.5 times 3 times 75. We got 0. Okay. So since this is a 1 degree, so this is actually then again a 2 degree curve. Okay. So this is a 2 degree curve and this is a 2 degree curve. And then it will end up at 0. Okay, so therefore, our shear and moment diagrams are correct. Okay. So, okay. So if you want to know the shear and moment diagram of this, we can actually write. But somehow, you can do it this way. Okay, already. Okay. So, what if? Okay. For just an additional knowledge. Okay. So we can also write its shear and moment diagram if you want. Okay. So we have, okay, we can divide this into 2 sections. The first section is from the support, okay? Let us say section 1, which is x is equal to 0 to x is equal to 3. So since we have, our shear here will be V, okay? V is equal to negative 230, and then your moment will be, since we have an initial of 690 here, so we got negative 690 plus 230x. So this will be your shear and moment diagram at section 1. Okay? Then you can use this to plot the shear and moment equations. Okay, I'm sorry. So since we have we have a distributed load, we got 230 minus 25x, and we got 230 plus negative 690, since we have initial value of 690 kilonewton counterclockwise. So we have negative 690 plus 230 times x minus 25x squared over 2. Okay? So please remember these formulas, okay? So if you I have been discussing this, okay, before. So, okay. Okay, so I hope you can see these formulas, okay? If you remember these formulas, I've been always using this, okay, in the previous examples in order to draw your shear and in order to construct your shear and moment diagram. So this is the part of your shear equation, moment equation, respectively, for distributed load and point load. Okay, so at this point, the distributed load, the value of its A is 0. So we get directly 25x squared, and then the reaction which started from the leftmost support or the leftmost side of the beam. So our A here is 0. Okay, so we have negative P. The A here is 0, so negative Px. And here the P is AY, which is 230. So we got 230x upward. Okay, so since it's upward, it's positive. If downward, it's negative. Okay, so these are the formulas. And then at section 2, x is equal to 3 to x is equal to 6, we got V, okay, so it's equal to 230. We already finished this 3 meters of 230, okay, minus 25 times 3, okay? Okay, so we have 25 starting, okay? So 230 minus 25, okay? X, sorry, 25x, and then we have this 80 minus 80 because it's point load, and then it's downward. So we got V is equal to 230, no, we got 150 minus uh, okay, so we'll check 150 minus 25x. So this is your shear equation. And then your moment will be 230. Okay, we have started negative 690 as your initial um, moment reaction at A. So we have negative 690 plus 230 x minus 25 x squared over 2. Then we have minus 80 times x minus 3. So I guess this is the shear and moment diagram. Okay, so you can locate actually any shear and moment even if it does not coincide with the changes in loadings. So we can, using these formulas, we can actually locate what is the value of shear when x is equal to 1.5 here, or your x is equivalent to 2, okay, which does not necessarily coincide with the changes in the loadings in your load diagram of your beam. Okay, so if we are going to check this when x is equal to 0, your shear is 230. Okay, and what if your x is equal to 3, we can get the value of your V. Okay, 230 minus 25 times 3 is 155, correct? And then the value of your 3 at section 2, okay, this is the first section here, 0 to 3, and the second section 3 to 6. So what if at the second section, okay, when x is equal to 3, 150 minus 2 times 25, 25 times 3, using this formula for shear, we'll get 75. So it's correct, 75. And what about if x is equal to 6? So, you use the equation at section 2. So, 150 minus 25 times 6, 0. Correct. Okay? And then, for your moment, we have these formulas. So, at section 1, when x is equal to 0, if this is 0, 0, it will cancel out. So, your m is negative 690. If your moment is equal to 3, you can actually get the value. Okay, let's check if it coincides. So, negative 690 plus 230 times 3 minus 25, 3 squared divide 2. So, negative 112.5. It's correct again. Okay, so what if x is equal to 6? It should be 0. Okay, so let us try. Negative 690 plus 230 times 6 minus 25 times 6 squared divide 2. Minus 80 times 6 minus 3. 0. Okay? So since we've got 0 at the end, at the right side, so these shear and moment formulas are correct. Okay? So that will be the end of our example. Okay? So we get it by area method. Okay? In which we get the changes in your load diagram and then make our shear diagram, and then the area under the shear diagram will be the corresponding value for your M, or your moment diagram. And then we can also draw your shear and moment diagram by using shear and moment equations. Okay, you can choose whatever is easier for you. Okay.